You're 25 years old, standing on Earth, looking up at the stars. You board humanity's fastest spacecraft and point it toward the cosmos. You say goodbye to everyone you know. The engines fire, Earth falls away. You have one lifetime ahead of you, maybe 60 years if you're lucky. When that journey ends decades from now, when you've lived your entire life aboard that spacecraft, how far from Earth will you actually be? The answer isn't what you think, and it reveals something profound about our place in the universe. Right now, the fastest object humans have ever built is screaming through space at 430,000 miles per hour. The Parker Solar Probe achieved this staggering velocity on December 24, 2024, making it the fastest human-made object in history. At that speed, you could circle the entire Earth in under 3.5 minutes. The probe reached this velocity through a series of gravitational slingshots around Venus, using the planet's gravity like a cosmic whip to accelerate itself deeper toward the Sun. So let's do the math. If you could somehow maintain that speed for 60 years of continuous travel, how far would you get? 430,000 miles per hour times 24 hours gives you over 10 million miles per day. Multiply that by 365 days, and you're covering about 3.8 billion miles per year. Over 60 years, that's roughly 228 billion miles. Sounds impressive until you learn that the nearest star system, Alpha Centauri, sits about 25 trillion miles away. You'd cover less than 1% of the distance. After 6 decades of traveling at the fastest speed humanity has ever achieved, you'd barely have left the solar system's neighborhood. You'd still have more than 99% of the journey remaining. The Voyager 1 spacecraft illustrates this problem perfectly. Launched in 1977, it's been traveling for nearly 48 years. It's currently about 15 billion miles from Earth, moving at 38,000 miles per hour. At that speed, Voyager would take roughly 75,000 years to reach Alpha Centauri if it were pointed in that direction, which it isn't. In all those decades, covering all those billions of miles, Voyager has barely scratched the surface of interstellar space. Here's where things get interesting though. The Parker Solar Probe didn't achieve its record speed through raw propulsion power. It used gravitational physics and fell toward the Sun. Chemical rockets, the kind we use for most space missions, can't exceed exhaust velocities of about 5,000 meters per second. They're fundamentally limited by the chemistry of burning fuel. You can't make a chemical reaction more energetic than the bonds between atoms allow. And those limits mean chemical rockets will never, ever get us to another star in a human lifetime. But what about more advanced propulsion systems? Ion drives represent a significant step forward. They use electricity to accelerate charged particles, achieving exhaust velocities tens of thousands of meters per second, far better than chemical rockets. NASA's Dawn spacecraft demonstrated this technology successfully. The problem is thrust. Ion engines produce tiny amounts of thrust, fractions of a newton. They can run for years, gradually building speed, but they take forever to accelerate anything massive enough to carry humans. Nuclear propulsion changes the equation. A nuclear thermal rocket heats propellant using a reactor instead of chemical combustion. This allows much higher exhaust velocities and could potentially cut Mars travel time from 9 months down to 3 or 4. NASA is actively developing these systems right now. With nuclear propulsion, you might reach a few percent of light speed given enough time and fuel. At 5% of light speed, you could reach Alpha Centauri in about 87 years. Too long for a single lifetime unless you left extremely young and lived extremely old. Fusion propulsion would be even better. Fusion seeks to replicate the sun's power, combining hydrogen isotopes to release enormous amounts of energy. It offers the highest theoretical energy yield of any propulsion system we can imagine building. The catch: we don't have controlled fusion yet. Despite decades of research and billions in funding, we've barely achieved fusion reactions that produce more energy than they consume. The National Ignition Facility achieved fusion ignition in December 2022, a genuine breakthrough, but the lasers required 300 times more energy to operate than the fusion reaction produced. We're making progress, but practical fusion power remains frustratingly out of reach, and fusion rockets would be even harder than fusion power plants. Then there's antimatter. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's famous equation. This is the most energy-dense fuel theoretically possible. With antimatter, you could accelerate to significant fractions of light speed with manageable mass ratios. The problem is, we can't make antimatter in meaningful quantities. CERN produces about 1/1,000,000,000 of a gram per year. At that rate, producing a single kilogram would take 10 billion years, longer than the universe has existed. We'd need to improve production efficiency by factors of millions or billions, requiring dedicated antimatter factories powered by a significant fraction of our civilization's entire energy output. So with current technology, you can't reach another star in a lifetime. With nuclear propulsion we might develop in the next few decades, you could maybe reach 1 or 2 nearby stars if everything goes perfectly. With fusion propulsion we might develop in the next century. You could visit several star systems within 10 or 20 light years. But the vast majority of our galaxy would remain forever beyond reach, unless you're willing to embrace something strange. Einstein's theory of relativity offers a loophole, but it comes with a cost most people would find unacceptable. When you travel at speeds approaching light speed, time passes differently for you than for observers back on Earth. At 50% of light speed, time runs about 15% slower for you. At 90%, it's dramatically slower. You could theoretically travel for 60 years of your own time and cover distances that would take thousands or millions of years at slower speeds. Under continuous acceleration at 1g, providing comfortable artificial gravity, you could reach the edge of the observable universe in less than a human lifetime. But while you age 60 years, billions of years would pass on Earth. The sun dies. Your civilization transforms beyond recognition. Your species might evolve into something unrecognizable or go extinct entirely. You step off the ship in a universe that's aged eons while you've lived a single human life. That's the bargain relativity offers. Distance for time. You can cheat space, but not history. Most people wouldn't take that deal. Leaving behind everyone you know is one thing. Arriving in a future where nothing you understood exists anymore is something else entirely. You'd be a ghost visiting an incomprehensible tomorrow. So let's set aside relativistic speeds and focus on what's actually achievable. What could you reach traveling at speeds we might realistically build within the next century? With nuclear thermal propulsion, traveling at maybe 3 to 5% of light speed, you'd cover roughly 2 to 3 light years in 60 years. That gets you close to Proxima Centauri at 4.24 light years, But you'd need the full 80-year human lifespan, and you'd have to leave as a child. More realistically, you could explore our immediate stellar neighborhood. Wolf 359 at 7.8 light-years becomes borderline reachable. Barnard's star at 6 light-years fits within the window if propulsion efficiency improves slightly. You're looking at a bubble maybe 5 to 8 light-years in radius. Perhaps a dozen star systems total if you're lucky and technology advances faster than expected. Push to 10% of light speed with early fusion systems, and suddenly, 60 years gets you 6 light-years. Now Barnard's star is definitely accessible. Sirius at 8.6 light-years becomes possible if you extend the journey slightly. Your reachable bubble expands to maybe 20 or 30 star systems. Still a tiny fraction of our galaxy's 400 billion stars, but at least you have options. 20% of light speed. That's 12 light-years in 60 years. Tau Ceti at 11.9 light-years. Epsilon Eridani at 10.5 light-years. You could visit several dozen stellar systems, potentially exploring 100 stars if you chain destinations efficiently. But here's what nobody mentions when discussing these speeds. Getting there is only half the problem. You also need to stop. Every calculation assumes you accelerate to your cruising speed, coast for the bulk of the journey, then decelerate at the destination. Deceleration requires just as much energy as acceleration. If you spend 35 days accelerating to 10% of light speed at 1g, you need another 35 days decelerating. That's 70 days total, where you're not at full speed, eating into your available travel time. The faster you want to go, the longer acceleration and deceleration take. At 50% of light speed, you'd spend nearly 6 months just speeding up and another 6 months slowing down. A full year of your 60-year journey consumed by changing velocity. And that assumes you have enough fuel. Remember the rocket equation. The more speed you need, the more fuel you carry. More fuel means more mass. More mass means you need even more fuel to accelerate that mass. The math spirals quickly into impossibility. Chemical rockets can't even begin to approach these speeds. The fuel requirements exceed the mass of available matter. Nuclear fission gets you to a few percent of light speed theoretically, but the engineering challenges are immense. You're carrying a nuclear reactor and enough uranium or plutonium to run it for years, while simultaneously shielding your crew from lethal radiation. Fusion would solve many problems if we had it, but we don't. Not even close. We can barely sustain fusion reactions for seconds in experimental facilities, consuming more energy than they produce. Converting that into a rocket engine that operates reliably for decades in the hostile environment of deep space remains science fiction. Some proposals suggest Bussard ramjets that scoop hydrogen from interstellar space and fuse it for fuel. Brilliant concept. Impossible engineering. You'd need a magnetic scoop thousands of miles across to collect enough sparse hydrogen atoms. The power required to generate those magnetic fields exceeds what the fusion reactions would produce, especially at the low speeds where you're starting out. Then there's antimatter, the most energy-dense fuel theoretically possible. Perfect conversion of matter to energy. You could reach significant fractions of light speed with reasonable mass ratios. Except we produce about 1/1000th of a gram of antimatter per year at facilities like CERN. You'd need kilograms. Creating that much antimatter would require dedicated factories consuming a substantial portion of human civilization's total energy output, running for decades. Even if you somehow produced antimatter in useful quantities, storing it becomes nightmarish. Antimatter annihilates instantly upon contact with normal matter. One containment failure and your spacecraft becomes a bomb brighter than the sun. You'd need perfect magnetic confinement running flawlessly for years. One power fluctuation, one system glitch, one micrometeorite impact that disrupts the fields, and everyone dies in a flash of gamma rays. So the propulsion problem isn't solved. Not even close. Which means the realistic answer to our question remains stubbornly limited. But propulsion is only the first obstacle. Space itself tries to kill you at high speeds. Interstellar space isn't empty. It averages about 1 hydrogen atom per cubic centimeter. Sounds incredibly sparse. It is. That's 25 billion trillion times less dense than air at sea level. But when you're moving at 60 million miles per hour, you sweep through billions of atoms per second. Each collision deposits energy. At 10% of light speed, each hydrogen atom hits with about half an electron volt. Individually negligible, collectively significant. Over years of continuous bombardment, the front of your spacecraft heats up from trillions of impacts. You need cooling systems, heat radiators, thermal management for a surface being sandblasted by atoms at relativistic speeds. Worse are dust grains. Interstellar space contains tiny particles of rock and ice, maybe one per few cubic miles on average. A grain 1 micrometer across, smaller than a bacterium, weighs about a trillionth of a gram. At 10% of light speed, that microscopic speck carries the kinetic energy of a bullet. It punches through your hull like artillery. At 50% of light speed, the same grain hits with the force of a high-powered rifle round. At 90%, several kilograms of TNT exploding, a single dust grain you can't see coming vaporizes part of your ship. You need shielding. Thick plates of material positioned ahead of the spacecraft to absorb impacts. But shielding adds mass. More mass means more fuel. More fuel means a heavier ship. The engineering margins get tighter and tighter until the whole enterprise collapses under its own requirements. Radiation presents another persistent threat. Cosmic rays, high-energy particles from exploded stars and energetic galactic events, permeate space constantly. On Earth, the atmosphere and magnetic field protect us. In deep space, nothing shields you. Astronauts on the International Space Station receive 150 times more radiation than people on Earth's surface, and they're still relatively close to home within Earth's magnetosphere. On a voyage to distant stars lasting decades, radiation exposure compounds relentlessly, enough to significantly raise cancer risk, potentially enough to cause acute radiation sickness during the journey itself. You need meters of shielding. Water works well, absorbing radiation while serving as drinking supply and oxygen source. Arrange water tanks around living quarters, and you get double functionality. But meters of water surrounding the crew compartment means thousands of tons of mass, just for protection. Add that to propulsion fuel, life support equipment, food stores, the spacecraft structure itself. The numbers spiral upward fast. Then there's the human factor. 60 years confined to a metal box. You can't step outside. Outside doesn't exist in any meaningful sense. Just vacuum and lethal radiation. You're sealed inside the same compartment, breathing recycled air, seeing the same walls, hearing the same machinery hum for decades on end. Antarctic research stations provide some insight into long-term isolation. People spend months cut off during winter when conditions prevent resupply or evacuation. Depression rates climb. Irritability increases. Conflicts emerge over trivial matters. The isolation and monotony wear people down psychologically. That's months, not decades. And those researchers can still communicate freely with the outside world. They know rescue remains possible if something catastrophic occurs. An interstellar crew has none of that comfort. Communication lag grows with distance. At 1 light year out, messages take a year to reach Earth and another year for any response. 2-year round trip for a simple conversation. At 10 light years, 20 years between question and answer. You might be middle-aged before hearing back from someone you asked something in your 20s. The conversations become letters to strangers in the future. You're fundamentally alone, disconnected from the civilization you left behind. If critical systems fail, if someone develops a medical emergency, if the mission encounters unexpected problems, no rescue mission can reach you in time. By the time help could be organized and dispatched, you'd be gone. Complete self-sufficiency becomes mandatory. Maintaining mental health under these conditions presents challenges we've never solved. Therapists, structured activities, virtual reality simulations of Earth environments might help. Art, music, whatever provides psychological relief from the crushing monotony. Whether that's sufficient remains unknown. We've never attempted to keep humans psychologically stable in isolation for 6 decades. The human mind evolved for open spaces, social interaction, connection to natural environments. Can we function properly sealed in artificial habitats for entire lifetimes? Maybe resilience exceeds our expectations. Maybe with proper support systems and clear purpose, people adapt. Or maybe after 20 or 30 years, even the strongest personalities begin deteriorating. Depression, anxiety, cognitive decline becoming inevitable consequences of prolonged isolation. The ethical implications get murky. You're essentially asking volunteers to accept potential psychological damage for the mission's sake. That might leave them broken, unable to function properly upon reaching their destination. The people who arrive might not be the same people who left, and not in a good way. So the complete answer involves more than propulsion and energy. Biology matters. Psychology matters. Human limitations matter as much as physical ones. You could theoretically build spacecraft capable of 10 to 20% light speed using foreseeable nuclear propulsion technology. You could theoretically shield against radiation and micrometeorites with sufficient mass. You could theoretically design life support systems that recycle everything efficiently for decades. But if the crew psychologically disintegrates halfway through the journey, technical success means nothing. Every component must function: propulsion, shielding, life support, and crew mental health. Failure in any domain dooms the mission. That makes interstellar travel extraordinarily difficult. Not impossible, but requiring solutions to problems spanning multiple disciplines. Engineering, medicine, psychology, all have to align perfectly. This brings us to time dilation, the one genuine escape hatch physics provides. Travel fast enough, and time itself becomes malleable. Einstein's special relativity predicts this, and it's been confirmed experimentally thousands of times. Atomic clocks on airplanes tick slower than identical clocks on the ground. GPS satellites must constantly adjust their timing to account for relativistic effects, or navigation would fail within hours. At everyday speeds, differences remain negligible. But approach significant fractions of light speed and time dilation becomes dramatic. The mathematics follows the Lorentz factor. Gamma equals 1 divided by the square root of 1 minus velocity squared divided by light speed squared. At low speeds, gamma stays close to 1. Time passes normally for you and for stationary observers. As velocity increases toward light speed, the denominator approaches 0. Gamma climbs toward infinity. Time slows down for you relative to everyone else. At 10% of light speed, time runs about 0.5% slower for you than Earth. 60 years for you equals roughly 60.3 years on Earth. Barely noticeable. At 20%, time runs 2% slower. 60 years for you, about 61 years on Earth, still modest. But at 50% of light speed, time runs 15% slower. 60 years of your subjective experience equals 69 years on Earth. The gap widens noticeably. At 70%, time runs 40% slower for you. 60 years for you, 84 years on Earth. A whole generation passes while you experience a single lifetime. At 90% of light speed, time slows dramatically. 60 years for you equals about 138 years on Earth. Everyone you knew would be gone. Your children, if you had any, would be elderly or dead. Your grandchildren would be middle-aged. The world would transform completely. Technology, culture, politics, everything different. You'd arrive as a visitor from the past, stepping into an unrecognizable future. Push closer to light speed and the effects become extreme. At 99%, 60 years for you equals about 425 years on Earth. Over 4 centuries pass while you experience 6 decades. The civilization you left no longer exists in any recognizable form. At 99.9%, 60 years for you spans roughly 1,340 years on Earth, more than a millennium. You'd depart in the 21st century and arrive in the 33rd. The transformation would be incomprehensible. Theoretically, you could travel arbitrarily far in your own lifetime by approaching arbitrarily close to light speed. Visit the galactic center 26,000 light-years away in 60 years of your time if you traveled at 99.999% light speed or so. Reach Andromeda 2.5 million light-years distant in a human lifetime at close enough to light speed. Even traverse the observable universe in principle, though tens of billions of years would elapse on Earth. This reveals the fundamental paradox of near-light speed travel. Physics permits you to cross cosmic distances within a single lifetime through time dilation, but only by severing every connection to the era you departed. You could journey to distant galaxies and return biologically young, yet arrive home to find Earth transformed beyond recognition. Your species might have evolved into something unrecognizable or vanished entirely. The sun could be dying or already dead. Everything familiar would exist only in ancient historical records if it's remembered at all. Most people wouldn't accept that trade. The psychological cost proves too steep. You'd sacrifice everyone and everything you've ever known for the privilege of seeing distant stars. Your family, friends, culture, civilization, all of it lost not to death, but to the relentless march of time. You'd become unstuck from your own timeline, a temporal refugee with no home to return to. So when evaluating practical interstellar travel for humans, we must constrain ourselves to speeds where time dilation remains modest. Speeds where decades pass on Earth instead of centuries or millennia, which means velocities of perhaps 10 to 30% of light speed maximum. enough to reach nearby stars within a lifetime, not enough to reach distant regions of the galaxy. Now let's examine what this actually means in concrete terms. With current technology, chemical rockets and ion drives, a human couldn't reach another star within a lifetime, not even close. Parker Solar Probe, our fastest spacecraft, moves at roughly 0.064% of light speed. At that velocity, reaching Alpha Centauri would require about 6,800 years. You'd spend your entire 60-year journey traveling less than 1% of the distance to the nearest star. Nuclear propulsion systems we could potentially build within the next few decades might achieve 3 to 5% of light speed. At 5%, you'd cover about 3 light years in 60 years. That's tantalizingly close to Alpha Centauri at 4.25 light years, but not quite enough. You'd need roughly 87 years for that journey. You could potentially reach Barnard's star at 6 light years if you lived exceptionally long and departed young. Fusion propulsion, assuming we solve the enormous engineering challenges within the next century, could theoretically push us to 10 or 20% of light speed. At 20%, Alpha Centauri becomes reachable in about 22 years. You could visit several nearby star systems within a 60-year lifetime. Barnard's star, Wolf 359, Sirius, all within range. You'd have dozens of potential destinations to choose from, but fusion remains theoretical. We've been pursuing controlled fusion for 70 years without achieving net energy gain. The National Ignition Facility achieved fusion ignition in late 2022, releasing more energy than the lasers delivered to the fuel pellet. Historic breakthrough, but the lasers themselves consumed 300 times more energy than the fusion reaction produced. We're making progress, yet practical fusion propulsion lies decades away at minimum, possibly much longer. Antimatter propulsion could theoretically achieve 30 to 50% of light speed or higher with remarkably efficient mass ratios. At 50%, you'd reach stars 30 light-years distant in 60 years. Hundreds of star systems become accessible. But antimatter faces catastrophic practical obstacles. We produce roughly 1/1000th of a gram annually at facilities like CERN. At current rates, accumulating 1 kilogram would require 10 billion years. We'd need revolutionary advances in production efficiency, improvements by factors of millions or billions. We'd need to solve storage problems containing antimatter without it touching normal matter and annihilating instantly. The engineering challenges dwarf anything we've attempted. These limitations define the realistic answer to our question. With foreseeable technology over the next century, a human could potentially travel 10 to 20 light years in a lifetime. That's the honest assessment. Not thousands of light years, not across the galaxy. Just a small bubble around our sun containing perhaps a few dozen to a few hundred star systems depending on their distribution. Our galaxy spans 100,000 light years. It contains hundreds of billions of stars. A 20 light-year travel radius gives you access to perhaps 100 millionth of the galaxy. The vast, overwhelming majority remains forever beyond reach unless you're willing to embrace time dilation and lose your connection to your own era. This feels limiting at first glance. Humans tend to want everything, to explore every corner, to push beyond every boundary. But consider what that 20 light-year radius actually contains. Real star systems with real planets orbiting them, potentially habitable worlds where life might exist or could be established. entire solar systems to explore, each one unique, each one offering different environments and possibilities. Within 20 light years, we've already identified potentially habitable exoplanets. Proxima Centauri b orbits in its star's habitable zone. We don't know yet whether it truly harbors life or even liquid water, but it's potentially habitable. Other nearby systems might contain similar worlds waiting to be discovered and explored. Even if we can only ever reach a tiny fraction of the galaxy, that fraction still represents more than any individual human could fully explore. Dozens of star systems, potentially hundreds of planets and moons, countless environments and phenomena to study. A lifetime wouldn't suffice to thoroughly investigate even one star system, let alone dozens. The question shifts from, can we explore everything, to can we explore anything beyond our solar system? And the answer to that second question is genuinely yes. We can reach nearby stars. We can visit other worlds. We can establish humanity's presence beyond Earth. Not everywhere, but somewhere. Perhaps that's enough. There's something profound about accepting constraints while recognizing possibilities within them. The universe has set boundaries. Light speed limits how fast we can travel. Human lifespans limit how long we can journey. Time dilation forces impossible choices between distance and connection to home. These aren't failures of imagination or engineering. They're fundamental properties of reality itself. Yet within these constraints, space remains accessible. The nearest stars lie within reach using technologies we could develop. Maybe not tomorrow, maybe not this decade, but plausibly within the next century. Fusion propulsion, advanced nuclear systems, perhaps even more exotic technologies we haven't conceived yet. The engineering challenges are immense but not necessarily insurmountable. So a human traveling through space in one lifetime could realistically reach 10 to 20 light years using foreseeable technology. About 3 to 6 nearby star systems with conservative assumptions. Perhaps dozens with optimistic technological progress. Either way, you're confined to the sun's immediate neighborhood in cosmic terms. But that neighborhood contains wonders enough to occupy generations of explorers. Real destinations, real possibilities, real opportunities to answer humanity's oldest questions about our place in the cosmos. The stars remain distant, but some of them, the closest ones, are within reach. You've been traveling for 60 years. The engines finally go silent. Through the viewport, a yellow star grows brighter. Planets orbit in the darkness. One of them might have water, might have life, might become home. You're 85 years old now, if you're still alive. Everyone you left behind on Earth is gone. But you made it. You crossed the impossible distance between stars. You proved it could be done. And somewhere behind you, other ships are following.